So dear students, welcome to another lecture of Basic Electrical Engineering. In this lecture, we will discuss about the various types of DC machines, and we will also derive the expression for the EMF equation in DC machine. So this lecture is dedicated to the discussion related to types of DC machine and EMF equation of DC machine for generator. And in case of motor, the same thing is known as back EMF. So we will see how do we get the generated EMF and back EMF, right? Now, as far as the classification of DC machine is concerned, as we already have discussed that a DC machine is the one in which uh, the electricity involved is DC, either at the input or at the output. Okay, a DC generator is the one which converts the mechanical energy into a unidirectional electrical energy. And a DC motor is the one in which the DC supply is provided and we get a rotation of the motor. That is, the DC electrical energy is converted into mechanical energy. So as far as the classification of DC machine is concerned, DC machines are basically broadly classified on the basis of how their field system is excited. In previous lecture also we have discussed this thing in brief, right? So how do we excite the field system? Now, when we say field system, we actually mean to say the how the magnetic flux is generated, where phi indicates flux. Okay, so if we connect the field winding, okay, so if the field winding is connected to a separate DC source, that means we are generating the magnetic flux through a separate DC source. And that is why this type of machine is known as separately excited DC machine. And then the second category is we have the self-excited DC machine. In self-excited DC machine, the field winding is connected to the uh, supply or connected to the voltage which is associated with the armature. If it is a generator, so we get the current in the field winding from the armature itself. If it is a motor, then we get the current in the field winding through supply. So the same source is used. We do not use a separate source or different source to generate magnetic field or to excite the field system. A field system is that system, that part of DC machine, which is responsible for the generation of magnetic flux or magnetic field. Then we have one third category, which is a permanent magnet DC machine. So in this, we make use of natural magnets to have the magnetic flux. So natural magnets are used. So by using natural magnets, we get the magnetic field or magnetic flux, right? And you will find such machines in toys, small toys, electronic toys, right? Like cars and all that, robots, cars, all that. Okay. So you can see these type of DC motors specifically in toys, right? Now, these machines are further have the categories like the self-excited. So separately excited is only one, permanent magnet is only one, but the self-excited is further categorized in three categories. The first one is the shunt wound, then we have series wound, then we have compound wound DC machine, or we can say shunt wound self-excited DC machine, series wound shunt self-excited DC machine. Then we have compound wound self-excited DC machine. Okay, so when I'm saying machine, I'm actually covering both generator as well as motor, right? Because as far as construction is concerned, as far as their circuit diagram is concerned, so both are similar. There is no difference between the construction of a DC generator and a DC motor. So a DC generator can act as a DC motor, or you can say a DC motor can act as a DC generator. So there is no specific difference. The only difference is that in generator we get the supply, in motor we provide the supply. Okay, so in shunt wound the field is connected in parallel to the armature. So here this field is in parallel to the armature. Here the field is in series with armature. Here we have further two categories. Field is in parallel with armature, field is in series with armature. So both are used, right? So we can say that this compound wound is further of two types, cumulative and differential. So cumulative is the one in which the flux generated by this series winding supports um, flux generated by the series winding supports the flux generated by the shunt winding, right? The winding which is in parallel. In differential, we have that the flux generated by series winding opposes the flux generated by the shunt winding. Okay, so we can say that this compound is of two types, cumulative and differential. Now, in this, we have further two categories, like we have long shunt and short shunt. Okay, so in cumulative as also cumulative compound DC machine, we have long shunt as well as short shunt. In differential also we have long shunt as well as short shunt. So both type of machines we have in compound wound. So this these categories which you are seeing on this slide are based on the excitation provided to the field system, or in very simple words you can say how the magnetic field is generated, magnetic flux is generated in DC machines. Okay, if the field winding is connected to some separate source, some source which is not the part of the DC machine, so we will call this type of machine as separately excited DC machine, either DC generator or DC motor, right? And if the current provided to the field winding of the machine from the armature, or the current which is associated with the armature, a part of that current is provided to the field winding, we will call such machine as self excited DC machine. Then we have compound, okay, permanent magnet. So self excited further has T category. So now let us see their circuit diagrams. Okay, so now first of all we have a separately excited DC machine. As you can see here, this particular symbol, this is a symbolic representation, a symbol of armature. So this is a symbol of armature, right? So these two are the brushes, this one and this one. So these are the brushes. This is also a brush, right? Okay, these two are brushes and these are the terminals, right? This is the field winding. Now, if the field winding is connected to some other source, and let us say this is the field voltage and this is some field current IF. So this field will generate the flux, and this flux will be associated with the what do you say, uh, the armature. And armature has the conductors. So when the conductors are in magnetic field and they are rotating at a certain velocity, angular velocity, so we will have certain EMF induced on the conductors which are placed on armature. Now if we put the current carrying conductors in the magnetic field as in the case of motor, so we will get the mechanical action or motor action, right? Now, as this is the symbol of armature here, now, okay, now you can see here how will you identify, because the same diagram is used for generator, or you can say DC generator and DC motor, then how will you identify whether it is a generator of the armature system, right? So that is why we call it as a separately excited DC machine. Similarly, then we have uh, the shunt wound DC machine. This is the part of self-excited, right? Self-excited. So uh, now in self-excited DC machine, the first part is shunt wound machine. So you can see in shunt wound machine, the field system is the part of armature system. That is, it is the inherent part of the DC machine. It belongs to DC machine, right? So when you provide supply, like in case of motor, okay, for example, this is V, so it is a motor case, for example. So in case of motor, the current will go and it will divide in these two branches, right? So the same current, that means the current which is been provided to the armature, a part of that current is used to excite the field system, or it is used to generate the magnetic flux or produce the magnetic flux. So that is why we call this as a self-excited DC machine. For example, if it is a generator, then in that case we have a different approach like this. So this is a generator, right? So these are the brushes, this is armature, so it will generate some EMF. Let us say this EMF is EG. So the current will be going like this. So this is the armature current IA, and this is the load current IL, and this is the ISH. ISH is the shunt current that is flowing here in this particular winding, and this is the field winding, right? So this is a field winding, so it will produce certain flux, right? So because the field is excited through the current which is generated by armature, the current is the part of armature and field is generated from that particular current, and that is why we call this as self excited. Now you can see the field is connected in parallel to the armature. Okay, so field, here you can see field system and armature system are in parallel to one another. That is why we are calling this machine as shunt wound DC machine. Then another uh, example of self-excited DC machine is the series wound DC machine. Now here you can see that this armature and this field are in series with one another. Okay, so armature and field are in series, right? So these are in series, that is why it is a series wound self-excited DC machine. So again, you can identify whether the given circuit diagram belongs to a generator or motor. So for that, you can see the direction of current. If the direction of current is from armature to the load terminals, yes, load terminals, so it would be a generator. If the direction of current is from the input terminals to the armature, then it is a uh, motor, right? So this was a series wound self-excited DC machine. Now another example is the compound wound. So in compound wound we have a short shunt and long shunt DC machine. Okay, so in short shunt you can see that we have a shunt winding. This is the shunt winding, and this is the series winding, right? So shunt winding and series winding. So the shunt winding is in parallel to the armature. However, series winding is in series with the supply or the load terminals, that is output terminals, right? So this is a short shunt type, a compound DC machine. Then another is we have long shunt. So in long shunt, you can see these both are in parallel to the supply. Okay, so shunt across supplied is written here also. That means this is the series winding, this is shunt winding. So both are in parallel to the input terminals or load terminals. If it is a motor, then these are the input terminals. If it is a generator, then these are the load terminals, right? You can also draw it like this one, this long shunt can be drawn like this. So you have series winding here, then you have brushes, then armature round circle, then another brush, and these are the terminals here. So in case of motor, these will behave as input terminals. In case of generator, these terminals will behave as load terminals, and this is another winding here. So this winding is this one, okay, and this winding is this one, right? So both windings are in parallel to these particular terminals, right? Okay, so that is why we are calling it as a long shunt. Now in cumulative and differential, the difference is that in cumulative compound wound DC machine, the flux generated by the series winding and flux generated by the shunt winding both assist each other, okay, or you can say the flux that is generated by series winding, you know, assist or supports the flux generated by the shunt winding. So in case of differential, the flux generated by the uh, series winding opposes the flux generated by shunt winding, right? So that becomes the differential compound, as you can see in these two diagrams, right? This is the cumulative compound DC machine, this is a differential compound DC machine. These both are the example of short shunt. Now what is the identification of short shunt? You can see that this particular winding is in series with the terminals, and this is in parallel to the armature. However, in long shunt, both are in parallel to the supply, but this series in series winding is in series with the armature in case of long shunt, right? So in differential, you can see the direction is here like this, and here the direction is this one. In this case, both have the same directions. So here they are assisting each other, both windings are assisting each other, their magnetic flux is assisting each other. But here in this case, their magnetic flux will oppose each other. So this is the difference between cumulative and differential compound wound DC machine. So this was about the classification of DC machines, right? In case of DC generator, in case of DC motor, in both cases we have the same classification. We do not have a different classification in case of generator and motor. The only difference is that the direction of current. While drawing the circuit diagram, you need to take care of the direction of current. For generator, the current will always be outside. For motor, the current will always be towards the armature, right? So now this is what you can see. For if the current is towards the armature, this one, so it is a motor operation. If current is outside, it is a generator operation. Okay. Now let us come to the next slide. So field winding. Field windings are used to generate the magnetic flux or magnetic field in the DC machine, because machines function or operate on the Faraday's law of electromagnetic induction. As far as generator is concerned, we all know that the generator action can only be obtained when we place a conductor in the magnetic field, right? So this is the magnetic field, this is a conductor, and we rotate this conductor in the magnetic field. So we will get an EMF on this conductor, which is given by E is equal to minus d phi by dt, right? Now for motor action, what is the principle? You have magnetic field, you have conductor, right? But this conductor is already carrying some current. So we have current carrying conductor placed in magnetic field. So this conductor will experience a force, and we will get some rotation because of the torque generated in this particular conductor. So this is the motor action. Okay. So now that means to have the generator action or the motor action, we need a conductor, we need magnetic field, right? In case of generator, we get the current. In case of motor, we provide current to the conductor. Okay. So in this, the field system, the field winding plays a very important role to get Faraday's law of electromagnetic induction implemented, right? So we have shunt winding, as already discussed. Shunt winding will always be connected in parallel to the armature, right? Shunt winding will have large number of turns. These are the high voltage winding, and their resistance is uh, high. Okay, and these machines, the shunt machines, are generally known as the constant speed machines. They have constant speed, right? So the voltage will be high across the winding, the resistance will be high, and the wire used to form the winding will be, because R is equal to rho L by A. So if R is high, the area of cross section is low, right? This is low. Okay, so that means thin wires are used to make the shunt winding. Then, as you can see here in this statement, only 5% of the rated armature current will flow through the shunt winding, and the reason is that their resistance is quite high. Okay. Then we have series winding. Series winding will always be connected in series with the armature, right? If you have an armature like here, okay, so this circle is the motor armature rotating part. These are the brushes, symbolic representation, and then we have series winding. So it is connected in series, right? So let us say RSE is the resistance of the series winding. So this is always connected in series with the armature. This is armature, right? So the resistance of this series winding will always kept low. Okay, and that is why the series winding is made up of thick wires. Okay, so you can use the same formula, R is equal to rho L by A. So if R is less, then A is high. Okay, so thick wires are used to form the series winding, because these windings are used in series with the armature, so their resistance is kept low, right? So to have the minimum voltage drop across these windings. Then we have short shunt. So in short shunt, the connection shunt field is connected directly across the armature terminals. Okay, so as you have already seen in previous slide, so in short shunt we have armature, and we have the shunt winding here like this. Then we have a series winding which is connected in series with the terminals here, right? So this is short shunt. Then we have long shunt. In long shunt, or uh, both the windings are in parallel to the supply or the input terminals or load terminals. However, the series winding will be in series with the armature. However, the shunt winding will be in parallel to the combination of series and armature. You have already seen in the previous slide. Now, this was about the field windings. Now, let us come to the EMF equation of the DC generator. So, now Uh, a DC generator is an electromechanical conversion device or an electrical machine which is used to convert the mechanical energy into electrical energy. So, to convert the mechanical energy into electrical energy, we need, because the working of a DC generator is based on Faraday's law of electromagnetic induction. So, we need the magnetic field to have the EMF, and then we need the conductor, right? And this conductor must be moving or rotating in the magnetic field and cutting the flux. So if it is happening, so we can get, as per Faraday's law of electromagnetic induction, we can get an EMF induced on the conductors which are rotating in the magnetic field. And the magnetic field in DC generators is usually the static magnetic field, right? So now let us come to the EMF equation. So let us consider that P is the number of poles in the generator. So poles are used to generate the magnetic flux. A pole consists of two components. One is the pole shoe, which is of this shape. The cross section view is this one, right? On this you have the field winding wound. This field winding will carry some current, which is DC current, which is either provided through a separate DC source. So we call such machine as a separately excited DC machine, or this current is the part of the armature current somehow. Okay, so so when we provide the current here, so by using right hand thumb rule, this curve rule basically, so we can easily find out the north pole and south pole in this case. Okay, so this pole shoe will act as one pole. So we may have two pole machine, four pole machine like this. Even number of poles will be there. So let us assume that there are p number of poles in a DC machines which are used to generate the magnetic flux. Then let us assume that phi is the flux per pole. That means each pole is producing a flux which is phi, and the unit of flux is Webers. Then let us say that we have, because We know that the let us consider two pole machine here. So these are two poles. So one of the pole will be acting as the north pole and another pole will be acting as the south pole, right? So let us say this is north pole, this is south pole, right? And we have field winding here. So, and this field winding is given some supply, right? So I current is flowing here. Okay, so this is the stator part. Now this is the armature part, rotating part here. So this rotor will have some conductors placed on its periphery. So there are some conductors placed here, right? So this rotor is rotating in the magnetic field. This is the magnetic field. So while rotating, these conductors are cutting the magnetic field. Okay, so to rotate this rotor in the magnetic field, we make use of prime mover. Fine, either it is a turbine or like that, something, some mechanism through which we have coupled or connected the rotor part of the machine, and we are rotating it in the magnetic field, right? So when these conductors which are placed on the periphery of the armature, these conductors will cut the magnetic field, so we will have the EMF induced on these conductors. So let us say that there are Z number of conductors present in the machine which are placed on the armature. Okay, so if we have number of slots, then we have number of conductors per slots will give you Z. For example, if we have 10 slots on this armature, 1 2 3 4 5 6 7 8, like 10 slots are there, for example. So every slot if has two conductors, so there are Z will be equal to 20. So there are 20 conductors in all which are available on the armature of DC machine, right? Then now this is rotating at some RPM n, okay? N is the RPM, rotation per minute. Then we have number of parallel paths here. Now in previous lecture also we have discussed about the parallel paths, right? So as far as the parallel paths are concerned, or as far as the armature winding is concerned, so based on the formation of armature winding, we have two types of windings. One is lap winding, another one is wave winding. So in lap winding, we have total number of parallel path equal to number of poles. However, in case of wave winding, we have A equal to 2 irrespective of the number of poles, right? Whatever is the number of pole, irrespective of that fact, the number of parallel path will always be 2. Then let us say Eg is the generated EMF per parallel path in the armature. Okay, so now in this diagram you can see here the concept of parallel path. Now this particular diagram belongs to a lap winding based DC machine, and this is for wave winding DC machine. As you can see here, we have you know, these many parallel path. So here the formation of wave armature winding will be a lap formation like this. However, in this case it will be a wave formation like this. As you can see here, this is a wave formation, right? So here, irrespective of the poles, like you can see here, no, south, north, like this. So irrespective of the number of poles, we will only have two parallel path. Okay, but in this case you can see we have these two poles here, so we have two parallel paths. If we have four poles, we will have four parallel paths. So this is how the armature winding is connected, right? And the, as far as application is concerned, the lap winding based DC machine is used for high current applications, while wave winding based DC machine is used for high voltage applications, right? Now, now the first is the average EMF generated per conductor. As per Faraday's law of electromagnetic induction, each conductor which is rotating in the magnetic field. So let us say that this is a magnetic field, and in this magnetic field we have a conductor placed. So this conductor is being rotated at a certain RPM, and let us say, so this conductor will have an EMF which is given by this particular equation, right? Now, the flux cut per conductor in one revolution. When this conductor rotates, completes one revolution, the amount of flux cut by this. Now, if we have P number of poles, and every pole produces 5 flux. So the total flux produced at once, at one time, in the air gap of DC machine is P5 Weber. This is the total flux which is produced by total number of poles, right? So that means if this conductor will rotate in the um, field flux, magnetic flux, sorry, in air gap we will have P5 flux. This much flux will we have. So that means in one rotation, one revolution, it has cut this much of flux. So d5 will be here equal to P5 Weber, right? Now, the number of revolutions per second, if n is in RPM, so in per second it will be n by 60. So this is number of revolutions per second, right? So now time taken for one revolution. If in 1 minute total n revolutions have taken place, so in dt time total 60 by n rotations, or you can say one rotation will take 60 by n seconds. This much time will be taken by conductor to complete one rotation in magnetic field. So dt here will be equal to 60 by n seconds. Then as per Faraday's law of electromagnetic induction, every conductor will have this much of EMF, right? So we will place d phi equal to n, this one p phi, and dt will equal to 60 by n. So when we do so, so p phi divided by 60 by n, so it will give us this equation. So this is the average EMF induced on one conductor when it completes one rotation in a given magnetic field where the total flux is P into phi. Now, this is for one conductor, but we have Z number of conductors, right? And in every parallel path, we have this much, means every conductor will share these many parallel path, right? So we can say that the total EMF that will be induced by Z conductors per parallel path, right, will be the total EMF induced in one conductor into the total number of conductors and divided by the number of parallel paths. So this is the general equation of the induced EMF or generated EMF in case of a DC generator. So it is P phi Z n by 60A, where P is the number of poles, phi is the flux per pole, Z is the number of conductors, n is rotations per minute, then A is the number of parallel paths. Okay, now for a lap wound generator, in lap wound generator we know that number of parallel paths are equal to number of poles. So if this is the case, then we can replace A with P, so we can cut these two factors. So this is the total voltage induced, or you can say total EMF induced or generated by such type of generator in which the armature winding is lap wound. Okay, so now in case of wave wound generator, you can see here the number of parallel paths are 2 irrespective of the number of poles. So if we replace A with 2 here, you can see if we replace A with 2 here, so in this case, you can see that we have this EMF induced in every path. Okay, so this was about the EMF generated in a DC generator, right? Based on which kind of armature winding is used, whether it is lap wound or wave wound, we have two different or separate equations for both type of generators. However, in general, the equation is P phi Zn by 60A, right? So each parameter has already been explained to you. Now let us come to the EMF equation in case of DC motor. Because the formation, the construction of a DC motor and DC generator is same. As far as construction is concerned, the DC motor and DC generator is same. So there is no difference between the as far as their circuit diagram is concerned, their classification is concerned. That means a motor can act as a generator and a generator can act as a motor. But in case of generator, we call such voltage as generated EMF, which is given by EG. And in case of motor, we call the same EMF as back EMF, because in case of motor, we do not need the EMF. We need the motor action, right? The purpose of motor is to convert electrical energy into mechanical energy, but because we are getting an EMF which opposes, which counters the supply voltage, right? So we call such EMF as back EMF. So the expression will be same, because every motor will have the same thing: number of poles, total number of conductors per parallel path, lap wound motor, wave wound motor, right? RPM. So the expression of the back EMF will be same, it is not different, right? But it is only the terminology that is used, because in generator we need the EMF at the output, which can be used. In case of motor, we do not need EMF, we need mechanical output. But because it generates the EMF, so we call it as back EMF. Now, why does a motor, DC motor, generates back EMF? That you need to understand. As you can see in this animation here, now we have provided a supply. This is the plus terminal, this is minus terminal. So this is the commutator here, and these two are brushes, right? This is a brush, this is a carbon brush, both are brushes, and this is the armature, and this is, both are poles, right? Now this is a north pole and this is a south pole, because the direction of magnetic field is here, like this you can see. Now when you provide a current to the armature of a motor, because you have a current carrying conductor placed in the magnetic field, so this motor will start rotating, and the direction of rotation will be given by Fleming's left hand rule. Now we have got the motor action, okay, but you can see here you have these conductors which are cutting the flux. So while rotating, these conductors are no doubt carrying current, but they are also cutting the flux. Now when they start cutting the flux conductors, so because of generator action, they will have EMF induced over them. Now this EMF, the direction of this EMF is given by Fleming's right hand rule. Now the direction of this EMF will always be opposite to the direction of applied voltage. And that is why we call this as the back EMF, right? Okay. So now you can note down this statement here. Fine. So the same conductors are cutting, which are carrying current, are cutting flux. So we will get the generator action, and hence an EMF is induced on these conductors, which opposes the main supply, main voltage, main EMF, and hence this is called as back EMF. Now, so the equation for this EMF will be same. So the equation will be EB. So here we are using a notation EB, where B is represents back. It is also known as back EMF or counter EMF, right? So it is same. It is same. It is not different. So this was all about today's lecture, and thank you so much, guys.